Hello everyone, welcome to my calculus lecture. In this lecture, we study the product rule and the quotient rule. First, we talk about the product rule. Let's let u equal to f of x and v equal to g of x be differentiable functions. Then f times g prime of x is given by f prime of x times g of x plus f of x times g prime of x. Or in terms of Leibniz notation, we have the following formula, same thing, okay? So derivative of uv with respect to x is derivative of u with respect to x multiplied by v plus u times dv by dx. Okay, that's the product rule. Now the name makes sense, right? So how do we know this is true, right? So, the proof is not difficult. To show you that, let me move to my notepad. Okay, so here's the proof of it. The product rule. Okay, so again, the product rule is what? F times G prime is F prime times G plus F G prime. Okay, so here uh, F times G prime, by definition, that's limit H goes to 0, Fg of x plus h minus 4 over h, right? So f times g of x plus h is limit h goes to 0. That's f of, by definition, x plus h, g of x plus h minus f of x times g of x all over h. Okay? So next, what we are going to do is, so we have f of x plus h times g of x plus h here, right? I'm going to subtract here uh, g of x plus h times f of x, okay? F of x, right? So I am subtracting a new term, right? From f of x plus h times g of x plus h in order to retain this equality here, right? Give and take. So, I'm subtracting this, so I have to add same thing. Again, give and take. Minus, we have f of x times g of x. Okay, all over h. So now you see that these two guys, right? They have a common factor which is g of x plus h. So what I'm going to do is factor it out, okay? Factor it out. So limit h goes to 0, all right? So if you factor it out, what's remained is f of x plus h minus f of x all over h times I am factoring g of x plus h out. Okay, here for the second part, so the remaining two terms, right? We see that like f of x in common, so I'm going to factor it out. So I have f of x times what's remained is g of x plus h minus g of x minus g of x all over h. Okay, now first part here, when limit of this, when h goes to 0, what happens? That's exactly f prime. And by the assumption, f prime of s exists, right? And then what's going to happen to this? Limit, okay, so maybe I should write it down, separately. So here's what we have. Maybe I'm going to put a box around what I'm going to write. Okay, so I'll use maybe different color. Okay, I think that should be big enough. So here's what we have. Okay, so limit of f of x plus h minus f of x all over h is nothing other than f prime of x. And by the assumption, this exists. Okay, and limit of g of x plus h equals, what is that? That's the same as g of x. Why? Because g, the function g, is continuous. How do you know it is continuous? It is differentiable by, the assumption, right? So g prime of x exists. So g of x is differentiable. And if you remember, a function is differentiable at a point, it is also continuous at that point. So differentiability implies continuity of the function g. Because of the continuity, we have this limit, okay? So g of, remember in case g is a continuous function, limit can go inside, right, of the function g. I mean, that's not really mathematical, the way of saying, but, you know, uh, that's easy to understand, right? So uh, maybe I should write that down. So when g is continuous, right? This is same as a limit g of limit. So limit can go inside the continuous function, So h goes to 0. Yeah, so easily speaking, right. So, these are the same thing, right? So, limit can go inside, right? So this equals to g of limit of x plus h. Uh, yeah, uh, and that's same as g of x, right? Okay, so this is because g is continuous. Okay, g is continuous, right? Because g is continuous. Okay, so we have this one. So these two limit of each one of them exist. So the same as what in this case the limit of this, which is f prime of x. Okay, and the limit of this is going to be just g of x. So we get that plus f of x times, right? This has nothing to do with the limit, right? So stay same. And the second part is also what is that? When h goes to 0, limit is g prime of x. So we proved the product rule here, right? So it's not bad at all, okay? Yeah, earlier, like, I was, uh, you know, hesitating to say something, but I don't know. The students can easily understand if I say, okay, you know what, G is continuous, the limit can go inside, the continuous function, but I personally don't like that kind of expression. I feel like when I say that something like it's not mathematical procedure, but it sounds like limit can work into like the function inside like. So anyway, I mean, it's not important, but as long as you can easily understand it, then it doesn't matter. Like whether I like it or not, that expression can be used, right? As long as uh, it's easier to understand. Okay, so yeah, never mind. Okay, let's get back to my lecture slide. So we know this product rule works. Okay, we proved it, just proved it. So let us take a look at an example. Now here's the example using the product rule. Okay, using the product rule, differentiate the following function. Okay, so we have a product of two polynomials. Okay, product of two polynomials. All right. So to work it out, I'm going to go back to my notepad. So here's example. Right. So we have this function here, x squared plus 2x minus 1 times x cubed minus 4x squared. Okay, 4x squared. So let's call it y. Let's call it y. So here dy dx or y prime, that's going to be, first we take the derivative of first the function here, right? Okay, so x squared. You know what, actually I'm going to use a prime notation. X squared plus 2x minus 1 prime multiplied by x cubed minus 4x squared plus x squared plus 2x multiplied by x cubed minus 4x squared prime. So this is the product rule, right? Okay, what I just applied is a product rule here. Okay, that's product rule. The one we just learned, right? Okay, so the first part, the derivative is what? That's 2x plus 2, negative 1, that's constant, so it becomes 0, right? Multiplied by x cubed minus 4x squared plus x squared plus 2x minus 1 times, that's going to be 3x squared minus 8. 2 comes down, 4 times 2 equals 8, 8x, right? That's the derivative of this, second polynomial, right? So as far as like differentiation is concerned, we are done, okay? So, you might want to just leave it like that, but I want to actually go further, okay? Multiply out and then like, the putting like terms together and then simplify, okay? So in other words, like I want to write the whole thing as a single polynomial. So we have here 2x to the power 4, okay? And actually there is a reason why also I want to do this, you will see in a moment, okay? Anyway, so let's continue. So 2x times x cubed, 2x times negative 4x squared, that's going to be negative 8x to the power 3x cubed. And now 2 times x cubed, okay? And then I have negative 8x squared. I do the same thing here. So first thing is 3x to the power 4x squared times this is negative 8x cubed plus 6x cubed, 6x cubed, right? Minus 16, is that right? 16, yes, x squared. And then lastly, negative x squared plus 8x. Okay, so let's put like terms together and then simplify. So x to the power 4 term, so these two guys, right? Okay, I have these two guys. Together, I have a 5x to the power 4 cubic term. So, I have a negative 8x cubed plus 2x cubed together, negative 6x cubed, negative 6x cubed. Here, these two, negative 2x cubed, right? Negative 2x cubed. So 6 to negative 8x cubed. Okay? Right. And now squared, square term. So negative 8, negative 16, right? So together that's going to be negative 24. Negative 24 minus 3, negative 27. Okay? So hopefully, let me check again. Negative 8, negative 16, negative 24, negative 3, negative 27. Okay? Negative 27. Yeah, I don't want to have like, oops moment later on. So I just want to make sure that, I'm doing it correctly, right? Now, x term, we have only one x term here, right? So that's going to be plus 8x. I think this is it. So hopefully I didn't miss anything, right? Okay, so assuming that that's the uh, final polynomial, okay? Now what I'm going to talk about next is that, in fact, this kind of case, although, the function is given by the product of your two functions, two polynomials, right? You don't necessarily have to use the product rule in this case, okay? What you can do without, so say, assuming that we don't know the product rule, we can still find the derivative. All you have to do is first multiply. Okay, so this is a, let me call it like maybe solution 2. Okay, solution 2. So first I'm going to multiply out these two, right? So what do you get? X squared times x cubed, right? So x to the 5, x squared times this, that's going to be negative 4 x to the power 4. And then now 2x times this, that's going to be 2x to the power 4. 2x times this, negative 8x cubed. And negative 1 times this is a negative x cubed. And then I have a plus 4x squared. Now we are going to simplify this by putting, the calculating like terms together, right? So x to the 5, x to the 4 terms. We have two of them, so that's negative 2 x to the power 4. And then x cubed, so I have a negative 9 x cubed. And then finally, I have a 4x squared, right? Okay, so what you have to do is y prime equals just using the basic the differentiation rules along with what the power rule, right? So we have a 5 x to the power 4 minus 8 x cubed minus 27 x squared plus 8x, and we get the same result. Of course, they are supposed to be the same. So by looking at this, you see that actually, that this second solution is easier, right? Simpler, okay, right? Than using the product rule. So then you might say, like, what's the point of using the product rule? Actually, product rule is not just for this kind of functions, but there are like functions, there are like functions which is given by the product of two or more functions, but there's no other way than using the product rule to find the y prime. Okay, here like I can't give you. I mean, I can't work on like such examples because we haven't got to those other types of functions so far. We have studied what the only like I mean most of time, not most of time, so far like we have dealt with only like polynomial functions, right? Okay. Uh, but there are other types of functions like sine, cosine, like trigonometric functions, and also exponential functions and logarithmic functions and so on and so forth, right? So, like for example, what if you have something like this? Okay, so y equals x squared sine x. All right, so let's consider this kind of function. How are you going to take the derivative? No other method, you know, but to use the product rule. Okay, and what about this kind of thing? Like say y equals e to the x times cosine x, something like that. In this case, also finding the derivative of y prime, we just have to use the product rule, knowing that of course what the derivative of e to the x and derivative of cosine x, right? We are going to learn those things later on, right? But I'm just here, my point is that product rule is necessary. Okay, very important rule. All right. Okay, so let me go back to my lecture slide. Okay, so next thing we want to study is something called the reciprocal rule, or it is also called the baby quotient rule. Actually, reciprocal rule is the official name, and baby quotient rule is something I coined, all right? But I actually like it. Anyway, so what does it say? Let v be g of x, right? So v equal to g of x be a differentiable function with g of x not equal to 0. Okay, g of x not equal to 0. In this case, right, 1 over g prime of x is given by negative g prime of x over g of x squared. Or in terms of Leibniz notation, is given by d by dx of 1 over v is given by negative 1 over v squared times dv dx. So that's the reciprocal rule, or my favorite name, baby quotient rule. Okay, so how do we know this? Again, the proof is easy, so we are going to prove that. So let me go back to my notepad. Okay, so here, proof of baby quotient rule. Okay, so you can kind of guess like from this name, there will be, the quotient rule, right? There is. So this is like a simpler version, okay, or special case of the quotient rule. All right. So what did it say? 1 over g prime of x that equals uh, negative g prime of x over g of x squared, right? So that's baby quotient rule. So we start from 1 over g prime of x, okay? What is it? By definition, that's the limit h goes to 0, 1 over g over x plus h minus 1 over g over x all over h. Now that equals limit h goes to 0, by definition, 1 over g of x plus h is its value is actually 1 over g of x plus h, right? Likewise, the value of this is 1 over g of x all over h. Okay, so how do we deal with this? Okay, how do we proceed? I'm gonna combine these two as a single fraction. We can do that by taking the common denominator, right? In this case, the common denominator is gonna be a product of these two, right? G of x plus h times g of x. So that's the common denominator. So g of x plus h times g of x, right? That's the common denominator. Then you have to multiply now what? 1 by g of x, right? 1 by g of x minus here, you have to multiply this 1 by g of x plus h. And we have it down here, h, right? Okay. All right, so this can be written as g of x minus g of x plus h over, this is what? This has a fraction inside the fraction, right? It looks complicated, but it is not. So how do we actually, simplify this? Well, all you have to do is to multiply. So, consider this whole thing as a single fraction, right? I mean denominator. Sorry, this, consider this whole thing as the numerator and h denominator, right? So multiply the numerator and the denominator by the same number. The fraction doesn't change, right? So multiply top and bottom by g of x plus h times g of x. Here also, same thing. Down here, I'm going to multiply by the same number here, right? Okay, so don't panic, right? Then what happens is that you can write this as a, so actually it's going to be what, h times g of x plus h times g of x, but we can separate it. So I'm writing this first separately, and then we have 1 over g of x plus h times g of x, right? So far, so good. So now, first one, when h goes to zero, you know that that's g prime of x. Second part, those also have a limit. I mean, limit does exist when h goes to 0. When h goes to 0, what happens? G is differentiable, so g is continuous, right? Okay, we talked about that earlier. So when h goes to 0, g of x plus h, the limit is g of x by the continuity. So we have g of x times g of x squared. So what we have here is that, oh, sorry, that I just realized that I misspoke, right? This is not, the limit of this is not the g prime of x. The order is, the opposite, right? So what I'm going to do is subtract negative 1, then that's g of x plus h minus g of x all over h times, I still have this guy here, g of x plus h times g of x. Okay, so we are almost there, right? So equals now, the limit of this is g prime. With negative sign, I have negative g prime of x over, when h goes to 0, g of x plus h goes to g of x by the continuity I mentioned earlier, right? And so g of x times g of x, that's going to be g of x squared. Okay, so we just proved the reciprocal rule, or my favorite name, baby quotient rule. Okay, so here's an example. Differentiate 1 over square root of x plus 2, right? So example, differentiate y equals 1 over square root of x plus 2. Okay, so this is exactly kind of a form that you will have to use the baby quotient rule to find y prime. Okay, so y prime in this case, this is g. Okay, that's the function g here. Okay, so that's g of x. Okay, so using the baby quotient rule, that's going to be negative, I'm going to repeat writing again, g prime of x over g of x squared, right? So that equals negative g of x is square root of x plus 2 prime over square root of x plus 2 squared. Okay? So really, in this case, all you have to do is to find the derivative of the square root of 2, because 2 is constant, so it goes away, right? Okay? So how do we find the uh, square root of x prime? Where we talk about this, earlier, right? In my earlier lecture. First, you have to write this as write this into a form, where you can apply, the power rule, right? In fact, the square root of x by definition, that's oh, I don't know why it keeps doing this. Okay, I must have touched something. Anyway, so that's x to the power 1/2. That's the definition of square root of x, right? Prime. So this is the form where you can apply the power rule. So using the power rule, that's 1/2 times x to the negative. 1/2 minus 1 is negative 1 over 2, which can be written as 1 over 2 times square root of x. Okay? So you can always do this. However, as you shall see, you will encounter the derivative of square root of x quite often. Okay, quite often when you study calculus. So you know what? Every time you do this, instead of doing this, every time, you better actually remember this. So that way, you can save your time and energy. So square root of x prime to emphasize, I'm writing in red. Okay, so 1 over 2 times the square root of x. So you better remember this. Okay, you better remember this. Okay, so going back to our example. So here, negative derivative of this is what? Negative 2 times the square root of x over square root of x plus 2 squared. Okay? In fact, this one also, you have a fraction inside the fraction. Okay? So multiply the numerator and denominator by the same number, 2 times the square root of x. You can write this as negative 1 over 2 times the square root of x times square root of x plus 2 squared. Okay? So we are done with the differentiation. Okay? Some of you might be wondering, do I have to expand this, right? Square root of x plus squared. Okay? Well, if you want to, you can, but the thing here is that, all right, in mathematics, you do something, if you, okay, if you think whatever you do will, result in some kind of a simplification, okay? So whatever you do something, and then, the outcome is going to be like something much simpler than the previous form, then you do it. If not, if things are going to be really messy, more complicated, then why bother? Okay. So one thing here, though, in mathematics, some people have a misconception about mathematicians or mathematics. One of the misconceptions is that like we mathematicians like complicated stuff. That's absolutely not true. We like things simple. So, in fact, in mathematics, the two words, simple and beautiful, they are synonyms of each other. Okay, so we like things simple. Simple is beautiful. Okay, remember that. Right. Messy, ugly, complicated, ugly. Okay, right. So I don't think the expanding this is going to make things simpler. In fact, it's going to be messier. All right, so we're going to stop here. Okay, going back to my slide again. All right, so here comes the quotient rule. Okay, the quotient rule. Right, so what is it? We have two functions, okay? So, the two differentiable functions, u equals f of x and v equals g of x. And we are going to assume that g of x is not equal to 0. For an obvious reason, you will see from the following formula, okay? Which we call the quotient rule. Basically, quotient rule is about the derivative of f over g. So, right, the function f over g. So f over g prime is given by f prime times g minus f times g prime all over g squared. Or, using Leibniz rule, Leibniz notation, it is given by the following, okay, right, expression. By the way, I just misspoke like a Leibniz rule, right? But actually, there is something called Leibniz rule. The product rule here. Yeah, I didn't mention, but the product rule is also called Leibniz rule, named after the Austrian mathematician who is also like a founder of calculus, right? Who founded calculus independently from Sir Isaac Newton. That's the guy, right? So this rule here is called Leibniz rule. Okay, I mean it's not important. You can stick to the product rule, but since I just by mistake mentioned it, so I just want to tell you that. Okay, so this quotient rule, we are going to also prove that. So I'm heading back to my notepad. Okay, so proof of the quotient rule. So if you read like, the, say, different like calculus textbooks, right? Okay, each book might, you know, present like, the proof of quotient rule differently. So, some books might just directly prove quotient rule, okay? What I like is, you can do that. I mean, again, using the definition, right? Not a problem at all. But what I personally prefer is first prove right. So, what I wanted to say is that you can directly prove a quotient rule, and then you can actually get that baby quotient rule as a special case of a quotient rule. Okay, so that's one way to approach it. Another way you can do, which is my preference, or what I like, is first prove baby quotient rule, because proof is simpler than the proving the quotient rule directly, which is still not difficult, but simpler. And then once you have that baby quotient rule, then using actual product rule along with the baby quotient rule, you can also get this quotient rule, you know, easily. So that's what I'm going to approach it, and some books do that too. Okay, so here's the thing. We have, so start from f over g prime, right? F over G prime. So this time I'm not going to use the definition, but this is, you can write this as what? F times 1 over G, right? F times 1 over G. So you can write F over G as the product of two functions, F and 1 over G. So you can use, in this case, product rule, right? Product rule. So I am using a product rule. So that's going to be F prime multiplied by 1 over G plus F times 1 over G prime. That's the product rule, right? So this equals, so I have F prime over G. And now, for the second part here, right, 1 over G prime, that's where the baby quotient rule comes in, right? So F times by baby quotient rule, that's negative G prime over G squared, okay? Right, so here I used baby quotient rule. So we have F prime over G minus F G prime over G squared. And so in this case, G and G squared, right? The common denominator is G squared. So we are going to combine them into a single fraction, G. So with the common denominator G squared, for that, I have to multiply F prime by G because you get G squared from here by multiplying G by G, right? So you have to multiply the same thing. G prime by the same thing, which is G. So I have F prime G minus FG prime. There you go. So this is the quotient rule, right? We just proved the quotient rule. Okay, it's easy, right? All right. So you might see why I like this one better. Anyway, again, I'm not going to say like which one is better, just my preference. Okay. Good thing about mathematics is as long as you follow the logic and you follow the laws and laws in mathematics, then the rest you can do whatever you like. That's so-called freedom of mathematics. Okay, so that's a very important thing. We do have a freedom of mathematics, right? Okay. Okay, so here's an example. Find the derivative of h of x, which is given by 2x plus 1 over all over x squared minus 2. So let's find the derivative of this, okay? Which means I have to go back to my notepad. Example. Find the derivative of h of x equals 2x plus 1 all over x squared minus 2, okay? So here's a solution. Using the quotient rule, Okay, so h prime of x equals 2x. Okay, so this guy here is f, and down here, this one here is g. Okay, so maybe I should. This is first time we're doing it, so I'm gonna write down the quotient rule first. So by quotient rule, that's f prime g minus fg prime all over g squared, right? G squared. So f prime here is 2x plus 1 prime multiplied by x squared minus 2 minus 2x plus 1 stays same and multiplied by x squared minus 2 prime. Okay, all over g squared, so x squared minus 2 squared. Okay, so that equals 2x plus 1 squared, 2x 1 prime, that's just 2 times x squared minus 2 minus 2x plus 1 times x squared minus 2 prime, that's 2x, all over x squared minus 2 squared. Okay, so I mean, as far as like derivative is concerned, we're done, but I think we can, simplify this, okay, a little further. So I'm going to actually multiply this out. I have 2x squared minus 4. Here, I have a negative 2x times 2x, negative 4x squared, negative 2x. Okay, so now 2x squared and negative 4x squared together, that comes down to negative 2x squared minus 2x, negative 4, okay, all over x squared minus 2 squared. Okay, or you can write this as I mean, it's not really making big difference, but since like a negative 2 is in common, so by factoring out negative 2, you can write this as x squared plus x uh, plus 2, right? Plus 2. So you can write it this way also, all over x squared minus 2 squared. Okay, anyway, that's the derivative, right? Uh, we obtained by using the quotient rule. Okay, now next example is differentiate x squared plus 2 over x to the power a. So, often, like, students, without thinking, oh, this is a fraction, okay? So let's use, a quotient rule. Actually, you can use a quotient rule. There's no law against it. Obviously, I mean, this is a kind of, the function where you can apply the quotient rule. However, that's overkill, okay? Because there is an easier way to do, right? So if you want to use a quotient rule, be my guest, okay? But I'm not going to do that. But here, actually we have encountered this kind of example previously, right? When we talked about the power rule. In fact, in this kind of case, you can rewrite that as a form where you can apply the power law. So you can simply use the power law, to find the derivative. So let me I mean, you probably know what I'm talking about, but let me work on that. I guess like I have a little bit of space left, but I think I can do it. So what was the function we had? X squared plus 2 all over x to the power a. I hope I got that correctly. Yes, I did. Okay, so let me go back. Okay, so this can be written as since x to the power 8 is common denominator, right, for both, so we can actually separate them. So this is x squared over x to the power 8 plus 2 over x to the power 8. So that says what? X to the power 2 minus 8, which is negative 6, plus 2 times x to the power negative 8. So why don't I actually call it y? So y prime in this case, we can find it using the power law. So using the power law, that's going to be negative 6 x to the power negative 7 minus 18 x to the power negative 9. Okay, or you can write this as negative 6 over x to the power 7 minus 18 over x to the power 9. Anyway, even if you use the quotient rule, you will end up getting the same thing, but this is much simpler. Okay, right. So this is it, folks. More details of my discussion in this lecture today can be found in my lecture note at the following address. Again, this is hyperlinked, so all you have to do is click on this link. Okay, click on this link to get there. All right. Also, like if you want to visit, my the main blogger site, where you can find other lecture notes. You all you have to do is just click on this word blogger, which is hyper linked as well. Okay. Thank you for watching and listening my lecture here. Uh, I'll see you next time. Bye bye.